is 2, and 2 is included, and it goes up to infinity. Now, if you had x greater than or equal to -3, and I'll just go ahead and give two solved ones, and x is greater than 2. We'll do it that way. Okay. So here's 2, and they're already solved. Okay. Put those on a working graph. So now do the final graph for that as well as the interval notation. Remember, this is the word and. You're looking for where your starting point is that's true for both and whether that starting point is included or not. And for the starting point to be included, it must be included with both. So where do we start? 2. And is 2 included or not?
No.
No. In this one it was. Not only did the pink line overrun it, so of course it was included because everything greater than 1 was included, but in the green line it was x was greater than or equal to 2, so it was included in the second one as well, therefore it's included in the solution. Here, the pink line overruns it, that's fine, that 2 is included in this first inequality, but it is not included in the second one. So it is still the starting boundary point. It's where our overlap begins. Our overlap begins at 2, but because 2 is not included in both of these, then it still has a parenthesis. Still the boundary point, but it's a boundary point that's not included. And so in this case, our interval notation would be to infinity. Okay. Remember that see why this working graph is not your final graph, because it includes all this other stuff colored in that is not actually part of your final solution. Okay. Now some people can go straight from this to the final graph. Okay. The working graph is not required, but if you're a visual person, like I am, it's a very useful tool for seeing where the actual overlap is. And not only where the overlap is, but what the boundary point is included or not included. So these are examples of ones that aren't just that chunk of the number line. These actually involve infinity. Okay. This prior example, the prior examples did not involve infinity. It had a number that was a left boundary and a number that was a right boundary, and it was that chunk of the number line, everything in between. While the individual ones went off to infinity, the overlap was stuck between two numbers. And that's because they were going in opposite directions. But here, they ended up going in both directions, and so your final solution is going to involve infinity. They're both going off to either infinity or negative infinity, as is the case sometimes. And you just have to know where they start. So you will have infinity or negative infinity in your answer. Okay. -5x is greater than -15, and x minus 15 is greater than -10. Okay. So treat them as separate linear inequalities, solve them each separately, and then put each of them together on one working graph to see how they interact. The only difference between solving inequalities and equations, the only mathematically required difference, is that if you're dividing away a negative coefficient, you must flip the symbol. Yeah, that'll change everything if you don't. Be very aware of that. Doesn't matter whether the answer is positive or negative, it's just a negative coefficient. Last step. I apologize for my phone still being on. I have to check. I don't know if I mentioned it, but I'm just in a situation where I'm taking care of an elderly relative. I've become a caregiver over Thanksgiving. So, many of you might have been in that position as well too, to kind of be on call. Okay, so we've got those two individual solutions. We put them on individually on the same graph to see how they interact. And where do they overlap? They don't overlap, yeah. They don't. So is there an intersection? No. They both have legitimate individual solutions, but that word "and" tells you what is the solution of the compound problem. What values of x will make them both true? Are there any values of x that will make them both true, that are true for both? But, well, it could be infinity on this side, but these solutions won't be true for this one, right? Yeah. There's infinite solutions for this one and infinite solutions for that one, but are there any they have in common? No. So for the whole compound inequality, is there any solution? No. There is no value of x that will be true for both of these things. Yeah, there's values of x that are true for that, and there's values of x that are true for that, but there's no values of x that are true for both. Well, 0 is an actual solution. Rather, it is the no solution. Right. So if you have a graph, this is your working graph. Notice how your working graph here is absolutely incorrect as your final graph. It's the working graph that allows you to see there's no overlap. And because of the word "and," that means no overlap, no solution. So your final graph is empty. There's no value of x, there's no overlap, and therefore you would either write no solution or the null symbol. Yeah. That's one, yeah. Oh, that's it, yes, yeah. The 0 with the slash through it, right. Okay with that? Okay. All right. So, -3 less than or equal to 2/3 x minus 1 less than or equal to 1. Just a quick example before we move on to unions, just because I want to, same thing with the fractions when you're solving. This is a compound inequality, because it's got two inequality symbols. It's in compact form, and even though the word "and" isn't there, this is "and." This means that 2/3 x minus 1 is greater than -3, and also that 2/3 x minus 1 is less than 1. So x is going to be in between. Once we solve for x in the middle, it'll be in between two boundary numbers. So you know you're going to have a chunk of the number line. When you have these, there's no infinity. Okay? You're going to end up with a left-hand number and a right-hand number. So, but you're going to use all your skills now from solving linear equations to kill the fraction and solve, instead of left-hand and right-hand side, you've got left, middle, and right. Now, killing the fractions, we got 1, 2, 3, 4 terms is normally the first thing you do, and that's fine. Be consistent. Multiply every term by 3, or 3 over 1. If you want also just to make, instead of 4 terms, 3 terms, you can go ahead and add 1, because that's not going to make you have to like deal with any fractions. If you want to just go ahead and add 1 to everything, because that'll kill the 1 here. So you'll have negative 2 less than or equal to 2/3 x less than or equal to 2. Right? And now kill the fractions. If you kill them first with 4 terms, that's fine. Or just go ahead and get rid of the addition because you're not dealing with fractions. Now kill it with 3 terms. Either way, your denominator is still 3. So this would be times 3 over 1 times 3.
Where did the negative 2 come
From adding 1 to all parts. Because I wanted to get rid of this minus 1. And I did that before I killed the fractions just to simplify things because these aren't fractions. Since these aren't fractions, I can go ahead and add 1 and I'm not dealing with fractions.
Okay, but I did it backwards. Is that okay?
What do you mean backwards?
I killed the fraction.
That's fine. As long as you did this times 3 and that times 3 and that times 3 and that times 3.
Oh, so that's not together. That's not all in one. No, right? Because that's a minus.
Right.
Okay.
Yeah. So right now it has 4 terms. If you want to kill the fraction first, great. That's consistent from everything we've done so far. Multiply all 4 terms by 3, or 3 over 1. There's no harm in moving this 1 away first because there's no other fractions, so I can go ahead and simplify. Now I have 3 terms, and now I kill the fractions. Either way. The whole point of killing fractions first is so that you don't have to deal with fractions, but moving this 1 doesn't make you have to deal with fractions. So if you just want to be consistent across the board, kill fractions first. That's what we've done from the beginning. That'll get you there. Okay. This is a little other little efficient means of things as you start to recognize, oh, I can do that without messing with fractions, and now I only have 3 terms to kill the fraction rather than 4. Okay. But either way is mathematically sound. So that's negative 6 less than or equal to 2x less than or equal to 6. Let's divide away the 2. On all 3 parts, giving you x is between negative 3 and 3. We know this is an and because the very nature of it doesn't say the word and, but this compact form means both of these things are true. X, read from right to left, x is greater than or equal to negative 3, and x is less than or equal to positive 3. You don't even need a working graph for this one. That literally says x is between those numbers. And it's included, the left-hand boundary point is included. The right-hand boundary point is included. Smallest is on the left, biggest is on the right, both are included, and your solution is in between them. All right with that? So in 2.10, these are intersections. These involve the word and or the implied word and if it's in compact form. The 3 possibilities you will have in doing these is that chunk of the number line. And if it can be written in compact form, it will be that chunk. It may not be written in compact form. But if it can be, that's that chunk of the number line. They're going in opposite directions, but they overlap as they cross. And that chunk is your answer. The other possibility is that they go in the same direction, and just the part where they're both overlapping, they're going towards infinity or towards negative infinity, and that overlap. So that answer will involve infinity. And the third possibility is they're going in opposite directions, but they don't overlap. They leave a gap in the middle, and which means you have no solution. Those are the 3 things that can happen. Now, the other thing besides and, the other type of compound inequality is called unions. Okay, so a union, and this is going to involve the word or when we get to the inequality part. But to visualize it, just with some discrete sets, if you have that set A of 1, 2, 3, 4, and 5, and you've got your set B, which is 3, 5, 7, and 9, Again, it can also be written just as set notation form. 5 elements in set A, and set B have 4 elements. Now there's 2 different definitions of the word or in English. Or can either mean one or the other, but not both. Okay? For example, if you're going to paint a room, you might paint it either blue or green. You're not going to paint it both. Okay? So the word or, should we paint that room blue or should we paint it green? And it's going to be one or the other. That's one definition of or in English. But another definition of or in English that is also the mathematical definition means that one or both. Okay? For example, do you want the vanilla or the chocolate or the swirl? Okay? So this or in math is about the swirl. Okay? Just chocolate, just vanilla, or mix them together, a swirl. Could be either. Or means either that one, or both of them together. So when we're talking about set A or set B, we're talking about anything that is either just in set A, such as the 1, 2, and 4, or just in set B, which is the 7 and 9, or the stuff that is in both of them, the 3 and the 5. So in math, that union, the or, means everything you're looking at, whether it's only in A or only in B or it's in both. Okay? This is the union of A and B, and it's written this way, A union B. Probably recognized that before when we did graphs and we were doing domains of functions. Okay? And we might have had the domain of a function. Oh, this section, and then it kind of jumps, and then you got another section. Okay? But everything was included in the domain. You just have to say, you use that little U to say, oh, but we got to jump over some stuff that's not in it. Okay? So the union of A and B is everything that you see before you. So in set notation, A union B would be the set that includes all elements of both sets. Now, if any elements that are included in both, like the 3 and the 5, those are part of the union too, but don't write them twice. Okay? So the union is just everything. It's 1, 2, 3 is in both, but we only write it once. 4, 5 is in both, but we only write it once. We've already got 3, we already got 5, and then we also have 7 and 9. Now, just like with the intersections, there's 3 possible things that can happen. You have the chunk in the middle, or you have them both going off to infinity, but only the part that touches, they both touch. And then you have no solution, where there's no overlap. For unions, you have 3 possibilities as well. Okay. So, let's do negative 10x less than or equal to 20, or 3x minus 4 is less than 2. So solve those both individually, and then put the 2 individual solutions on a working graph so we can see how they interact. this could be the same problem as one we did earlier. The only difference is the word or instead of the word and. If this were the word and instead of or, if this were and, then what would our solution be? Just the overlap, just between -2 and 2. Okay. However, this is the word or, which means everything's included. The chocolate, the vanilla, and the swirl. All of it. Okay? Then, so when you draw your graph, what values of x can x be? This is the working graph. It's not the final graph because it's a mess. With brackets and parentheses, we no longer need. So what would we do to the graph of the solution of this union? What can x be?
Infinity.
Yeah, x, there's nothing x can't be. Right, x is everything, infinite. So on our graph, we would color in the entire graph. All values of x are good because they're going to be true for either this one, or both. Now, how do we write that in interval notation? What's the smallest possible value? And the biggest one? Positive. Just like when we did domains, many of our domains of functions in chapter 8 were infinite domains. All values of x were possible. Such as with lines. Lines had infinite domains. You might also see this written, though, as all real numbers. So you could write it as one or the other. That's what it means in interval notation and just in words. All real numbers. X can be anything. Solve two individual simple linear inequalities. Put them together on one working graph. To see how they interact. And the nature of their interaction is going to depend on this little word, and or. The solution depends on that word. If this was the word and, what would our solution be? No solution, exactly. There's a gap, there's no overlap. If this were the word and, we could have the same problem with the word and we'd say no solution, no overlap, nothing in common, no intersection. But this is the word or. So what's our solution?
No solution.
Would it be negative infinity, 9, and negative 3?
Right.
Positive infinity?
Yeah.
Everything you're looking at, right. Now we have a gap, this stuff's not included, so we have to show that there's a gap with that u. The solution is two intervals, this interval and this interval. Okay. So this is the working graph, but truly the final graph looks exactly the same. It is -9, and -9, neither of these are included, so it'll be parentheses for both of them. And they are diverging away. There's no overlap. There is a gap. So, but because of the word or, if it were and, it'd be no solution. Because of the word or, everything's included. We got chocolate, we got vanilla, we don't have any swirl, but it doesn't matter. The mathematical word or means anything you see is part of the solution. So you start from left to right with the smallest value, come up to where you have a break, that -9 is not included, we jump to -3 not included, all the way to infinity.
Is it later that you that was one of my questions. Is it later on that you're going to show us when and why you get the U either faces up or
Oh, well, facing up is union, like the word U, union with the U. Facing down means intersection.
okay.
Yeah, it's just one or the other. Here's the intersection. If you see this, this means A intersect B. That means you only want overlap, things in common. Okay? And A union B means everything's included. Yeah, so with compound inequalities, you got one or the other. You got the intersection or you got the union.
So basically the facing down is for the and then if it's or, the question is or.
Exactly. Yeah. And this one makes sense because it's like the word union. The other one is just the opposite of it. Is the other thing besides union is the intersection. Yeah. Now, just like for intersection, there were three possibilities: either that chunk of the number line with no infinity, or both going in the same direction, so something with infinity, just the part that they both covered, or no solution because there was a gap. There's three possibilities for union as well. They're both going in opposite directions, but they overlap. We don't care about overlap. That just means everything is part of the solution because of the or, all real numbers. Or they're both going in opposite directions, but there is a gap. Not a problem with the word or. It's just two different intervals that we glue together with the U to show that there's a gap. So the third possibility is, just like with intersections, is they're going in the same direction. Okay. So let's do 6 times x minus 2 greater than or equal to -12, or 4 minus x less than or equal to 10. Solve them as simple linear inequalities separately. Graph them separately on one graph. And then refer back to the little word in between. Is it and or? And what does that tell you about the solution? Zero is a legitimate solution. 0 is a real number. 0 is a legitimate boundary point. As long as your x doesn't disappear, your answer could be positive, negative, or 0.